School. Okay, everyone, please join me in welcoming Professor John Tsai.
Thank you. Thanks for that introduction, and I'm very pleased to be here to speak to you today. As you heard, the title of my talk is Mathematical Flexibility, a Promising Focus for Research and Practice. And just to give you an introduction to the structure of the talk, I'm going to begin by giving you an introduction to the construct of flexibility through a discussion of some mathematical examples, as well as to talk about research and context related to flexibility. I'm then going to speak about how existing research measures and conceptualizes flexibility. And then I'll speak to the benefits of flexibility, how we'll be able to foster its development, and then I'll close by sharing some thoughts on the next steps in the investigation of flexibility. My plan is to talk for about 1 hour, and then I'll look forward to answering any questions that you have. If you have any questions in the middle of the talk, feel free to raise your hand and ask, although I may ask you to save it till the end of the talk. And just to follow up on what you heard, I just wanted to introduce you to me a little bit. So as you heard, I'm a professor at Harvard, and I've been there for 18 years. My scholarly interests are around math education, where it intersects with educational psychology. And I am also a secondary math teacher. I did so for 6 years before my PhD, and I've recently returned to teaching mathematics at the what we would call middle school level in grade 8. This is what I've been doing for the past 7 years. In addition, for the past 10 years, I've been collaborating with many Chinese scholars and PhD students, both in educational psychology and in mathematics education in Beijing and in Shanghai, and I hope to add Macau to that list. So when you see me go through my publications in the talk, you'll notice there's a lot of Chinese-looking names, and those are all Chinese students that I've worked with in the past. And as you may know, I'll be here for a couple of weeks and would love to meet and talk with anyone who wants to meet with me at that time. So let me jump in by talking about the terminology that I'll be using when I talk about flexibility. So clearly you're going to be hearing me use the terms flexibility and procedural flexibility and strategy flexibility a lot in this talk. And let's say for now that I'm using these three terms synonymously, that they all mean the same thing as flexibility, although I'll get more into that in a moment. The second terminology thing I want to mention is that there's a difference in English between what some people call flexibility and some people call adaptivity. When I define what I mean by flexibility in a moment, I'll introduce this distinction as well. And the third terminological thing I want to mention is there's this other thing that some people call cognitive flexibility. And this is different than procedural or mathematical flexibility, but again, I'll talk about that more in a moment. So let's move to some mathematical examples that illustrate what I mean by flexibility. And I'm going to begin by looking at these two linear equations and consider the ways that these two equations can be solved. So for this equation, as with all equations, there are many ways that one could solve it. And here I've shown you two ways. The one on the left, which in many countries around the world would be considered a standard algorithm for solving this problem, and it's explicitly taught as such often. And there's a strategy on the right that we might consider to be a better way for this problem. This second strategy might be considered a better way because it has fewer steps, or you might consider it to be more efficient. Mathematicians might use the word elegant here as well, where elegant, which is a very difficult term to define, might mean a strategy that's optimally matched to the mathematical structural features of the problem. But note that when I change this problem slightly, as you see here with the 15 changing to a 14, both of these strategies can still be successfully used. But we might have an interesting conversation now about which strategy is the best. Is the strategy on the right still the best because it has fewer steps? Or is the strategy on the left better from the perspective of a student because it involves fewer operations with fractions? We know that operations with fractions are time-consuming and frequently full of errors for students, and so we may wonder whether that makes this strategy on the left better. The point here with this example is not that we all agree on which strategy is best. Rather, what I'm trying to illustrate here with these problems and the ones I'll show you next is that there are lots of different strategies that can be used to solve a problem, and we can engage in an interesting and nuanced but important conversation about which strategy might be the best for a given problem. So here's another example, and I can make the same point. The strategy on the left could be considered the standard algorithm for this problem, but because of the particular mathematical structural features of the problem that I show here, the strategy on the right can be used. And the strategy on the right is arguably better than the one on the left. So again, we see problems solved in multiple ways with an interesting conversation that we could have about which strategy is better for which problem. Similar situations arise throughout the mathematics curriculum, and here I show you 3 problems. We would call these proportion problems. Each is solved with a different method. The problem on the left is solved using a strategy that in the US, students often call cross multiplication. And this could be considered a standard algorithm because it applies to all such problems. But by changing one number from the problem on the left to make the problem in the middle, I've created a new problem that can be solved in a different way that I've represented with the up-down arrows. In particular, I can think of the ratio of 3 to 15 and say that 3 times 5 is 15, and so this must mean that 4 times 5 is 20. So x must be 20. And finally, with a different change of a single number, I create a situation where, looking horizontally, as indicated by the left-right arrow, I can use yet another strategy. I can say because 3 times 7 is 21, 5 times 7 must be 35. All 3 strategies work for all 3 problems, but the up-down strategy is better on the middle problem than it would be on the problem on the right, and the left-right strategy is better for the problem on the right than it is for the middle problem, all because of the numerical mathematical features of each problem. And some more examples. These are problems that involve fractions. As you can see, on the left, I have a fraction addition problem, and on the right is a fraction multiplication problem. And depending on how we're working on these problems, there may be standard ways to solve them as well as better ways. On the left, you can see that by recognizing the first and the third term as being very easy to add, as well as the second and the fourth term being easy to add, we can simplify this problem in a way that's better. And on the right, we can see that by recognizing the repeated 13/10 terms, we can solve this in a different and a better way. With integer simplification, the strategy on the left is where I might just move from left to right, and that might be a standard way to solve problems like this. But by switching the order of the terms, by commuting them, we can make the additions and subtractions much easier to do. So again, I'm illustrating here that there are multiple methods. Some are better than others, depending on the particular structural mathematical features of a problem. Now, the examples that I've shown you so far have all been in domains that I have researched, but I wanted to show you that there's another domain that others have researched, although I haven't. And here, these are integer subtraction problems that in many countries, students are taught to do these mentally. I don't study this domain because we don't teach this anymore in the US, unfortunately, but in many countries they do. And in this research literature and in these countries where this is taught in this way, there are many different strategies that students are taught that they're supposed to choose based on the number features of each problem. And so this is an example that I show you here, that students might notice particular features of a problem and choose a strategy accordingly. So with these examples in mind, I'm ready to move to a formal definition of flexibility. I define flexibility as having two parts. First, having knowledge of multiple strategies, and second, the ability to select the most appropriate strategy for a given problem in a given problem circumstance. Now, there's two additional points I need to make with regard to this definition. First, I mentioned earlier that some researchers in this area use the term adaptivity instead of flexibility, and now I can tell you what that means. For these researchers, the first part of my definition, knowledge of multiple strategies, is what they call flexibility. And the second part of my definition, the ability to adaptively select the most appropriate strategy, that's what they call adaptivity. So I collect both of these features together under the name flexibility, but others name them as two distinct qualities, the first flexibility and the second adaptivity. And the second point that I make here is that the notion of appropriate strategies, as in selecting the most appropriate strategy, is unavoidably nuanced. And I'll speak more about this in a minute. My interest in flexibility doesn't come out of nowhere, but instead connects with many different issues and themes and research traditions that come out of mathematics, mathematics education, and psychology. So let me take a few moments and talk about the context and related research in these different disciplines that informs the way I think about flexibility. Let me begin with mathematics education. So in the English-speaking world, there's a long-standing interest in what people often call procedural knowledge and conceptual knowledge. Here is a table that I included in a 2005 publication where I first introduced my ideas of flexibility. What this table is intending to show is the following. On the horizontal axis of the table, I've represented knowledge quality, where knowledge can be considered either to be superficial or deep, and deep is the desired outcome. On the vertical axis, I've represented the type of knowledge, and here the types we're talking about are knowledge of procedures or knowledge of concepts. At the time I wrote this paper, I believe that the common usage of the phrase conceptual knowledge indicated deep knowledge of concepts, or in other words, conceptual knowledge was considered to be a universal good thing, always. And the common usage of the phrase procedural knowledge indicated superficial knowledge of procedures only, implying that procedural knowledge was rather straightforward, easy to acquire, not nuanced, and in the US, almost a necessary evil. As I became interested in the outcome that I now call flexibility, it became apparent that there was no language that we could be using to refer to this deep way of knowing procedures. And this is what I started calling flexibility, to capture this, since I didn't find another way to refer to it using the conceptual and procedural knowledge terms. Now, in the discipline of mathematics, there are also some arguments for flexibility. In particular, as I alluded to a moment ago, the discipline of mathematics is concerned not only with arrival at a correct answer, but fundamentally how one has arrived at the correct answer. Methods of solution or methods of proof are evaluated as to their aesthetic qualities, including their elegance. Now, this word elegant, as I said earlier, is notoriously difficult to define, and mathematicians can have serious disagreements about which of two methods of proof are most elegant. But even though elegance is difficult or perhaps even impossible to objectively define, it nevertheless plays a critical role in the discourse around mathematics among experts in the domain. Now, we typically do not go so far as to use the word elegant when we're talking about elementary or secondary students' solutions to problems, but I would argue the idea is the same. Mathematics as a discipline cares about how one has arrived at the answer. Getting the right answer is important, but so is doing the mathematics in a sophisticated, clever, elegant, beautiful manner. Furthermore, students can participate in the discourse of mathematics by engaging in conversations and debates even about which methods are most appropriate or most elegant or best for a given problem or problem-solving circumstances. These conversations are deeply mathematical, and my point here then is that flexibility is important from a disciplinary perspective. And finally, situating this work in the discipline of psychology, we find several research traditions that strongly relate to and provide grounds for our investigation of flexibility. First, there's a long-standing distinction in psychology between what psychologists call competence and performance, where essentially competence is what you know and performance is what you're able to do. There's compelling evidence that students possess knowledge that they are not consistently able to utilize in what they do. In other words, psychologists would argue that competence tends to precede performance, and I think this is true for flexibility as well. There's also a very rich history of research in psychology on the development of children's strategies. Here I point to the work of Siegler and colleagues on strategy repertoire and strategy selection. So this is related to my work on flexibility. In addition, as I alluded to earlier, there's a literature on what has been called cognitive flexibility. I don't find this construct to be particularly well defined, and it's much broader and more general than what I call flexibility. But as I'll talk about in a moment, this literature does help us think about the underlying mechanisms that may support flexibility, including one or more aspects of what psychologists call executive functioning. And finally, I wanted to mention that maybe many of you are familiar with the literature on variation theory, which is quite well known here in China, and the work that's been done on Chinese teachers' use of variation. Certainly there's work here that's related to my interest in flexibility. Now, I want to switch gears for a moment to think about flexibility, but to do so, I'm going to invoke a metaphor. I'm going to switch out of mathematics for a bit, and I'm going to talk about another domain. And so think with me, this is a thought experiment. Think with me for a moment about any tools that you may have in your home. And I'm going to start by thinking about a hammer. Perhaps you have a hammer at home that you have a need for at other tasks that you do. A hammer is a general and powerful tool that can accomplish many sorts of tasks. And that's why you probably have a hammer. But do you have more than one hammer in your house? More than one type of hammer? Well, let's think for a moment about this. Why might it be useful to have more than one hammer at your house? Well, one reason is that if you lose your hammer, then you have another hammer that you can use. That's a good reason to have it. But perhaps more importantly, if you believe that you will encounter a variety of situations that require a hammer, and if you believe that different hammers will be differentially effective in these different kinds of situations, then you may feel it's worth it to have multiple hammers. But having multiple hammers comes at a cost. It's a cost monetarily because they're expensive. It also might be a cost in terms of storage space. Where do you put all of these hammers? And so you may feel that the benefits of having multiple hammers don't outweigh the cost of having multiple hammers. But that's not all. You also have to think about the ability to switch hammers if you think switching would be a good idea. So maybe you're working on a task on your porch with one hammer and it's not going so well. But your second hammer, you don't know where it is. It's buried somewhere in all of your stuff. Is it worth it that you stop what you're working on and you go searching for the other hammer to switch? Well, it's got to be a much better hammer to make it worth it for you to switch. If it's only a little better, then it's not worth it to switch. But if it's going to be a lot better, then maybe it's worth the effort to go try to find it. Consider what would happen if you decided that you needed to go to a store to buy a new hammer. That would suggest that it's not going so well with the hammer that you have, and that it's so much better with a new hammer that it's worth it to go out and get it. It'd have to be a lot better to do so. So there's this cost-benefit analysis that you are doing to decide whether you need to go and use a second hammer. So I've talked about the idea of having multiple hammers as well as the factors that underlie your willingness to switch hammers, but there's also the issue of how you figure out which hammer is the best. And that's not trivial. So perhaps you don't know a lot about a hammer, and I don't know a lot about hammers, and perhaps I don't know a lot about the variety of hammers that exist. But I can think about what are the features of hammers that might help me figure out what hammer is the best. So perhaps there's features of hammers such as how heavy they are, or how big their pounding surface is, or how long their shaft is. So there's features of hammers that might help me figure out whether that hammer is going to be best for this task. There's also features of the task I'm engaged in. So what am I hammering? What type of nail? How big is it? How heavy is it? I also might think about my goals in the task. Sometimes when you're hammering, you have to make sure you don't make a mistake. Maybe the thing you're hammering is very fragile, and you have to be careful that you don't break it. So not making an error is critical. But in other tasks, your job is to be efficient as possible, and you don't worry so much about making a mistake. And those are considerations of the task that help you decide which hammer is best. This is a complicated space that perhaps you hadn't thought about. And maybe when I talk about all this stuff with hammers, some of you might be thinking, I understand everything he said, but I still just think I just need one hammer. For the tasks I do in my house, one hammer is enough. I don't experience enough variety in the tasks that I do to make another hammer worth it. So that's reasonable. What you're saying to me is that you don't value flexibility in hammers because of the tasks that you experience. They don't require it. But if you feel that way, I would ask you to think about another domain now, which is screwdrivers. So even if you only have one hammer in your house, I would guess that you have more than one screwdriver in your house because you've decided that for the tasks that you experience, some screwdrivers are clearly better than others, and it's worth it to have multiple screwdrivers. So you value flexibility in screwdrivers more than you do in hammers. So with this discussion of tools in your house in mind, let's return to mathematics. So central to flexibility in mathematics is that an individual knows a variety of strategies. As you saw from my examples, algorithms exist for solving all sorts of problems effectively and efficiently, like the general purpose hammer. But a flexible solver has additional strategies that they know, strategies that they believe are potentially useful for the problems they see because those different strategies are differentially effective for those problems. So a good solver has to believe that knowing multiple strategies is a good idea because the strategies are differentially effective for different problems. The solver has to believe that the costs in terms of ease of learning or execution are not prohibitive, it's worth it. And they actually have to know those strategies that they could use. The flexible solver also needs to be able to switch strategies. So let's think about all that I said with hammers and switching strategies. Switching strategies could be related to the features of the solver's cognitive or executive functioning system. Some solvers just have an easier time switching than others. And so the third thing about flexibility here that I talked about, and this came up in hammers, is that we have to figure out which strategy is most appropriate for the problem that we're working on. Appropriate might mean that the strategy is the best fit with the structural or mathematical features of the task, and you can think back to the examples that I showed. Appropriate could also mean that a strategy, when executed, meets some desired personal criteria like efficiency or error-free execution or ease. And appropriate could also be related to broader things that an individual or even a culture values. What makes a strategy appropriate? So in thinking about these features of flexibility, and I hope I've convinced you that there's some nuance here, we need to think about how we might measure it. As a researcher interested in flexibility, it's essential that I not only precisely define what I'm interested in, but also that I have a good and reliable way to measure it. So I'm going to think about measurement with you for just a moment. So if I wanted to measure flexibility, what do I need to measure? I need to be able to figure out first whether a solver is able to switch, because I care about whether they switch strategies, and I need to be able to measure that. Well, how can you figure out if a solver is switching? Well, one way is that you could give them a very, very hard problem where they get stuck and they can't solve it, and then you see if they switch to another strategy that helps them be more successful. So this could be switching through an impasse, but at the same time, I could design a study where I essentially force them to switch as a feature of the study methodology. Like I could say to them, solve this problem, and once they finish, I could say, now solve it again, but use a different way. And so I'm essentially, as a feature of the study, inducing them to switch. Another way I could do this is I could show solvers a problem that's partially solved with an unfamiliar strategy and then ask them to complete it. So they don't know the strategy and they have to figure out how to use it. And there's another strategy that is used in this literature that some psychologists call the choice-no-choice paradigm, which is where I give solvers a set of problems to solve, and I tell them what strategy to use. They don't have a choice. And then I give them other problems to solve where they have a choice. And then by comparing their solution times and their accuracy on the choice trials versus the no-choice trials, I can learn something about what strategies they know and whether they are able to switch. So another feature of assessing flexibility that I need to work with is whether multiple strategies are used at all. So you might think, well, that's easy. If I want to know whether solvers use multiple strategies, I just give them a set of problems to solve, and then I collect their paper and I count how many strategies they used. And that tells me whether they know multiple strategies. But this is tricky, because if I give students a set of problems to solve, there may be good reason why they use the same strategy on all of the problems. And so I may conclude that they don't know multiple strategies from that, but they actually may indeed know multiple strategies. They've just decided not to use those multiple strategies on the problems I've given them. So I have to be very careful about how I look at and select the problems I'm using on an assessment when I give them a set of problems. Another way I could look at whether multiple strategies are used is by looking within the same problem. So I could do what I alluded to a moment ago, where I could ask them to solve a problem in multiple ways. And then I could see whether they're able to do so. And that would tell me whether they know multiple strategies. And then the final thing that I need to think about when measuring flexibility is how the flexibility is demonstrated, and this really relates to this idea of appropriateness. How can I tell whether they use appropriate strategies, whether they know appropriate strategies, what they mean themselves by appropriate strategies? This is important for me to know as well in assessing flexibility. So this is hard. This is hard to figure out how to measure flexibility, and I've gone through multiple iterations in my work on flexibility to try to figure this out. So let me talk to you about some of these ways that we've tried to measure flexibility. The first I alluded to a moment ago, which is through what a lot of researchers call the choice-no-choice paradigm. And again, this is where students have a set of problems where they have a choice of strategies, and they have a set of problems where they don't have a choice. and I can figure out something about their strategy knowledge and repertoire and choices by looking at their reaction times for how quickly they solve problems and also their accuracy. I mentioned that I don't use this method in the work that I do. This method is most used for people that study flexibility on problems that can be solved very quickly because it relies on reaction time. So think about those mental subtraction problems I showed you a few slides ago. This is where they use the choice, no choice methodology. But for algebra equations, for example, that might take a minute or two to solve, this method doesn't work, I think, because it relies on reaction time, and a minute or two is not a reaction time. There's a lot that could happen in a minute or two. So I began by doing what I called an alternative ordering task as my first way to assess flexibility. And what I did in this task, I gave students a problem to solve, and then I asked them to resolve the same problem but using a different strategy. So I did some studies on this, and this turned out to be useful because it did tell me something about students' knowledge of multiple strategies. But think back to my definition of flexibility, knowledge of multiple strategies, and this idea of strategy appropriateness, and the alternative ordering task gave me very little information about strategy appropriateness and students' knowledge of which strategies are most appropriate. And so I developed another way to assess flexibility with my colleagues from Beijing. And so in 2017, we published this paper where we reported on what we called the tri-phase flexibility assessment. And this assessment has been used a lot since then. And the way this works, we give students a set of problems to solve. It's tri-phase, so there's 3 phases. In phase 1, students are just asked to solve the problems. After completing the problems, in phase 2, they're asked to solve them all again, but using as many different ways for each problem as they can think of. So they solve each problem in multiple ways. And then finally, in phase 3, they are asked to circle the strategy among the ones they generated that they think is the best for that problem. So this assessment gives us information about students' knowledge of multiple strategies. As well, we have some explicit information about which strategy they think is the best. It's the one they circled. But interestingly, we also have some implicit information about which strategy they think is the best, because the strategy they think is the best implicitly is the one they use first. And so it gives us some interesting data about the relationship between which one they think is explicitly best, the one they circled, and which one they think is implicitly best, the one they use first. Sometimes those align and sometimes they don't. Now, there's been other recent work where we've tried to go even further and come up with some more nuanced ways to think about flexibility. I'll give you an example from my work here. So we had an assessment that involved a lot of these ideas that we kind of put together in a different way. So we gave students a bunch of problems to solve. After completing these problems, we had them resolve each problem in one additional way. Then we gave students 3 correct methods that we provided to them for each problem, and we asked them to tell us whether those 3 methods were similar to the ways they used. So they rated for similarity the methods we gave them with the methods they used. Then we asked them to rank the goodness, which ones are best, 1, 2, 3 for each of those. And then we also asked them to circle which one they thought was the best in the ones that they did. So hopefully everything I just said you've heard me mention before. This was sort of a composite measure of flexibility that we tried to do. And I think there's still work for us to do on really understanding what flexibility looks like, but it's essential that we know how to measure it well. And that's what we work a lot on, trying to refine those measures. Now, at this point, I'm realizing I haven't devoted a lot of attention to justifying the importance of flexibility empirically. And I have 2 things to say about this. First, an argument can be made that flexibility is an outcome of interest in students' mathematical learning just on its own. In other words, it may not be necessary to show that flexibility helps you achieve other outcomes, Like in your case, for example, it may not be necessary to show that students with higher flexibility have higher Gaokao scores, for example, because we may say that flexibility by itself is the goal. And I think we can make that argument. But even if we make that argument, there would be a more powerful argument that we would make if we can show that flexibility helps you with your performance in other areas. And I'll say that this is something that we continue to explore, and sometimes we find good relationships between flexibility and task performance, and sometimes we don't find the strong relationships that we hope for there. But intuitively, I do believe there is such a relationship. So I've spoken a lot about flexibility so far, and now that you know what it is, I'd like to talk about how to promote it. How do we get students to be more flexible? Because that's the whole point of this. We think flexibility is important, and so we want students to be more flexibility. Now, we are beginning to know a lot about flexibility now after maybe about 20 years of research in this area, and I'm just going to mention a few things that we are beginning to know. So we believe that flexibility improves with age, and that as students get older and learn more math, they become more flexible. We know that students with higher math ability tend to be more flexible, and that higher math anxiety may be associated with lower flexibility. We know that higher self-efficacy is associated with higher flexibility, and that aspects of executive functioning, as I mentioned a moment ago, do seem implicated in the development of flexibility. Now, there have been fewer intervention studies exploring flexibility. Some have existed, and so, for example, one study that I found really interesting, the one by my colleague Jiang there, it found that students who experience a slight delay between when they see a problem and when they're allowed to start working on the problem are more flexible. So imagine that I show students a problem to solve, I put it on the board, and for some students, they can start immediately. But other students, I say, you are not allowed to start for 10 seconds. And they can't pick up their pencil, and then after 10 seconds, I say, go, and then they start working. So in this study, he found that the students who had to delay a moment, they used a greater variety of strategies, better strategies, they showed greater flexibility. And he claims here that it's because when you are being flexible, you often have to inhibit the first thing you think of, the first strategy you think of. It may not be the best one. And that inhibition is hard. Some people, it's very hard. By giving this delay, that helps them inhibit that response and enables them to be more flexible. So that's interesting. But there's been other research that's explored other aspects of this. The one that I'm going to speak the most about here is sorry, I didn't put this up. That's where you see the Zhang reference there. The studies that I'm going to talk about more in depth in a moment are the last bullet there, and they're my own studies where we've designed an intervention specifically for improving flexibility, and we call this Comparison and Discussion of Multiple Strategies, or CDMS, and it's been quite effective, and so that's what I'm going to talk about in more depth in a moment. And I'd also like to direct your attention, if you're interested in this, in 3 recent reviews of flexibility that have just come out. The first one I wasn't a part of, by my colleague Lieven Verschaffel, but then the second 2 were by me and my team, where my colleague Wang and my colleague Yang are both Chinese PhD students, or were at the time. So let me move now to talking about the work that we've done on this intervention for improving flexibility that we call Compare and Discuss Multiple Strategies. The underlying premise of this work is that comparing and contrasting, comparison, is a powerful and key learning process. There's been a great deal of psychological research indicating that comparison helps learning in a lot of disciplines, including in mathematics. And in addition, comparison plays a big role in the teaching of mathematics, in that we know that expert teachers tend to use comparison more regularly, and that teachers in higher performing countries tend to help students compare more than in other countries. So in this work, we set out to explore and demonstrate the benefits of comparison for math learning by isolating this practice and studying it. And as I show in this graphic, we worked with students in two different conditions. One group of students learned to solve some algebra problems by seeing two problems and two strategies side by side on the same page, which is what you see on the left here. And there were questions asking them to compare and contrast the methods on that page. The second group of students saw the same problems, the same strategies, the same number and types of questions, but the problems were presented on separate pages, what we call sequentially, which I show on the right. And the questions did not prompt students to compare. So this was the only difference between the groups of students, is that some saw things on the same page and some saw them on separate pages. And it turned out that the students who compared had greater gains in their flexibility than the students who did not compare in the sequential condition. So this was our first study from 2007. And we did a series of studies confirming and extending these basic results. We then turned these materials into a curriculum, an algebra curriculum for teachers, and we showed teachers how to use it, and we studied those teachers' students, and we found, as we had hoped, that teachers who used our comparison materials had students who had improved flexibility. We then did a major revision of these materials to try to make them even better and more teacher-friendly. And we did another large study, and we found similar things. And so everything I just said there, that was about 10 years of work. But let me show you where we ended up. So this is a page from the curriculum that we ended up with for teachers. And this was what we would call a supplemental curriculum. This wasn't the teacher's main textbook. This is what they used at some other times. And let me point out some features of this to you. So you'll see here that there's two hypothetical students. Their names are Emma and Layla, and they're asked to solve a problem. And they do it in different ways. On the left, you see Emma's graphing way, and on the right, you see Layla's using algebra way. And in each of those ways, you see the student's math work, and then you see the student's dialogue, often in student language. You also see questions at the bottom that are asking the students in the classroom questions that help them process and understand these two strategies. You also see that at the top left corner, there's a question. It says, why does it work? And this is the kind of example this page represents. It's a why does it work, meaning that our goal in this example was for our students to compare and contrast these two methods and build flexibility, but also conceptual knowledge about these two strategies and important mathematical principles that underlie them. There were 4 different flavors of these examples, and this is one of them. I'll show you the second one now. So this one, if you look in the upper left corner, it's called How Do They Differ? So this is a slightly different version where these two students are looking at a problem solved with 2 different representations, and they're comparing and contrasting the representations. Again, with questions at the bottom that are asking students to compare. I'll also point you to this website that's listed at the right, which is where all of these materials are listed, are available freely for download. So this curriculum that we developed, it had about 70 of these pages that teachers used throughout the year, throughout the curriculum. And we had a particular way that we wanted teachers to use these materials that came from our prior studies that we thought was the most effective way to use our materials. We offered teachers professional development both in the summer before the study and during the school year to help them use these materials the way that we intended. And we offered this in the form of workshops for teachers. So I wanted to show you one piece of material that we introduced teachers at this workshop because it shows our vision for the ideal way to use these materials. We told teachers that the ideal way to use these materials for each of those pages, it ideally would take about 20 minutes, although teachers could do it more quickly or slower, depending on their own goals for their lesson. The 20 minutes began with what we called the compare phase, where teachers would engage students in preparing to compare, and preparing to compare often meant just looking at one of those strategies for a little bit, and then looking at the other strategy for a little bit. And then they did comparisons, which is the second make comparisons phase, where they were asking students to compare them. That led to a discussion phase, which was the 12-minute phase, where teachers began with what in the US we call a think, pair, share routine, where students are first asked to think by themselves for a minute, and then they talk to their partner for a minute about what they're thinking, and then we have a class conversation, a sharing. And then they continued with this think, pair, share to talk about what this example represented and what its point was. And then we had a whole class conversation about this as well, where the teacher identified what we called the big idea, which was what the instructional point was of that example. So if teachers use this pedagogical routine frequently during the year, as well as our materials, not every day, but they use them frequently. And we found, as I said, that teachers who used our materials had students who learned more than teachers who did not use our materials, which is what we were hoping to find. So we continue to be thinking about this line of work, about comparing and discussing multiple strategies. I would like to point out, though, that though we're happy and proud that our particular intervention, those pages you saw, worked, this is not the only way, or even perhaps the best way, to develop flexibility in students. There may be other ways to do so. We focus on comparing as an important way to help students develop flexibility, but there may be other ways that are worth exploring as well. So there's nothing magic or perfect about our intervention. It's just one initial step that seemed to have worked well. All right, so for the last bit of my talk, I want to talk about my current work as well as next steps in flexibility research that are promising both for my team, but also for anyone else who's interested in pursuing this kind of research. First, I have come to believe that there are some really interesting and important cultural variations and cultural influences on flexibility. And this, in part, drives my interest in forming collaborations with people from other countries, and I'm especially interested in the case of China. I've been fortunate enough to study flexibility in many countries and have published work where we talk about the flexibility of students from Spain and Sweden and Finland and China, and the US as well. I'm going to speak for a minute about the cases of Spain and China for a moment to show what I think might be going on in terms of one aspect of cultural variation. So I did this study where I assessed students' flexibility using that tri-phase flexibility assessment that I spoke about a while ago, and I gave the test to students from many countries. So when I gave it to the students from Spain, recall that in that tri-phase flexibility assessment, students were asked to solve a set of problems, and then they were asked to solve them again, but using different strategies, and then they were asked to circle what they thought was the best of the ones they produced. So when we looked at the Spanish students' paper and we scored their work using our scoring coding system for flexibility, we discovered that the Spanish students had low flexibility. And then we looked at the Chinese students, and we discovered that the Chinese students had high flexibility. And that was quite interesting for us. But then when we looked a little more closely at the papers, we noticed something very interesting. When you looked at the typical Spanish paper, and let's say there were 10 problems on this sheet. When we looked at the typical Spanish paper, for the 10 problems, and we looked at how they solved them and which strategies they thought were the best, they tended to rely on the standard algorithm for these problems on all problems. They would use it first. They would circle it as the best. So that's why they got low flexibility in our scoring system, because they never used, or they infrequently used, and they infrequently circled the more innovative, appropriate strategies. So we said, oh, they're not flexible. But then when we talked to the Spanish teachers made a very interesting point. They say, well, actually, the standard algorithm is the best strategy for many of these problems. The way that we teach it, the standard algorithm can be used on all the problems without thinking much. You can just use it without looking at the particulars of the problem. You can execute it very quickly and very fluently. And for the Spanish students, very accurately. They were extremely accurate and extremely fast on the standard algorithm. Then when we looked at the Chinese students' papers and we looked at how they solved the 10 problems, the Chinese students fit more closely with, at that time, our model of what flexibility should look like. They used lots of strategies. They would often use the one that we thought was the best strategy. They were very good at that. But for the Chinese students, in the phase 2, where they were asked to solve the problem in multiple ways, many Chinese students just didn't do that part. They left it blank, or they only wrote one other strategy. And when we asked their teachers and we asked the students, why did you do that? The Chinese students would typically say, well, what's the point of putting additional strategies on there? You asked me to solve it, and I used the best way the first time I solved it. That's the only way that matters. It doesn't really matter that you have other strategies that you know, as long as you can solve it with the best way. And at the time, in our coding system, that earned them a high score for flexibility. But we started to wonder, is that really being flexible? And so I think there's some really interesting cultural variations in flexibility that we're starting to get a handle on, that I continue to want to explore. So this is the first area of work that I'm currently doing, but also think there's a lot more interesting things to explore. The second issue that I'd like to discuss that I'm interested in is what I call transfer of flexibility. In my studies of flexibility so far, we have studied flexibility in one domain for that study. So maybe I have a study of flexibility in linear equation solving, or flexibility in calculus. But what we haven't explored is whether, if you're flexible in one domain, whether that makes you more flexible in a subsequent domain that you study. So if you demonstrate flexibility in algebra equation solving, if I then assess your flexibility 2 years later, are you going to be more flexible than your less flexible peers? Does it carry over? Does it transfer? And I don't think we know the answer to that question. I think we want to hope that you are, but we don't know. We've started to explore this a little bit, and my colleague Yang has an interesting study that is under review now, where he explores what he calls strategic mindset in mathematics. And what he did is he looked at a psychological scale that they called strategic mindset, and he adapted it to mathematics. And he was interested whether students who are more flexible, whether they, in addition to knowing multiple strategies, they just have a way of thinking that makes them more flexible. That maybe they think, oh, it's a good idea to always be looking for new and better strategies. And maybe some students just think that way about math, and other students don't. And he wanted to know whether those students who think that way, whether they demonstrate more flexibility. And I think his results suggest that there's some initial emerging evidence that maybe they do. And so I think this is very interesting to me. In much of the talk, you heard me speak about cognitive factors that are important in flexibility: knowledge of multiple strategies, knowledge of the most appropriate strategies, but there's also metacognitive aspects to flexibility as well. Beliefs about mathematics and beliefs about mathematical problem solving, and maybe something about mindset. And that's something that I think is very interesting and important that we also want to be studying. So a third interesting area that I have questions about is the relationship between what I call flexibility and what we could call fluency. So what I mean by this is, if we want students to know and use multiple strategies, that's flexibility. To what extent is fluency with a single strategy a prerequisite? So in other words, if a student becomes very fluent in a single strategy, does that help them later on be more flexible, or does it impede their flexibility? So for example, some students could become very fluent with a single strategy, and that makes them less flexible later on, because they think, well, I don't need to know more strategies. I'm really good at this strategy. It always works. I'm just going to use that one. I don't have to think about it. Or you could argue the other side. You could say, by becoming fluent in that one strategy, then that's a base from which they can build on and develop knowledge of more strategies. So I don't know which of those is true. And I don't think we have evidence either way. We have some slight hints in a really early study that I did, but I think we need to do a little more work on this, because I think that's very important. We do value both of those. Which one should we focus on first? I wanted to mention also that I have been studying flexibility in a number of domains, but there's still many other domains worth investigating in flexibility. So I mentioned here a few projects that I'm excited about that are happening right now. So I have an interesting project with a student who's visiting in my lab from Beijing Normal on area estimation flexibility. I have a student who's doing a study on flexibility in non-routine problem solving. And then I also have a student who's doing work on the relationship between flexibility and creativity, which is something I think is different than flexibility, but that's what she's exploring. So what I'm interested in here is that some mathematical domains prove to be quite easy to study flexibility, and some mathematical domains are just very hard to study flexibility. So that's interesting to me. What is it about a domain that makes it easier or hard to study flexibility in? And that's something that I think we can continue to explore as we study flexibility. And finally, I wanted to highlight some work that I have that explores students' opportunities to learn to be flexible. And this is about textbooks. So I have a student who's looking at textbooks in China and in the US, and ways in which they include opportunities for students to become flexible, and how the prevalence of those opportunities and the types of those opportunities might differ across the countries. I'm also interested in studying what teachers do in the classroom that promotes opportunities to learn flexibility, to be flexible. That's another area that would be interesting to pursue. So there's lots of stuff to study with flexibility, and there's lots of work that we're continuing to do, but also opportunities for independent work and collaboration as well. So I'm going to stop there. Thank you very much for your attention and for inviting me to speak, and I look forward to your questions.
Thank you very much, Professor Staff. You give us a very clear definition to flexibility and share with us many different ways to assess flexibility and to improve mathematical flexibility. I believe the audience may have quite some questions. Who will be the first one to ask? Yes.
Yeah, the first question. Students are really shocked. Very insightful presentation, thank you. I'm quite intrigued by your notion of mathematical flexibility. So I'm wondering what is the nature of mathematical flexibility. It is a trait like construct, or is it more competence or performance like construct? If it's more trait-like, and then mathematical flexibility would be more stable, would be more generalizable across domains, right? For example, algebra, geometry, statistics, and so on. If it's more performance or competence like construct, and then it's very dependent on what problem you're going to have, right? Or what domain it's going to have. What do you have found in your research?
Thank you. That's a great question. So I'm not sure we have data that explicitly helps us untangle those two. And so I'm relying as much on my experience and intuition as actual studies to answer your question. But I feel like there are components of both. And I know that both is sort of it's not the best answer because it's sort of saying it could be both. But I'll say why I think it could be a trait, but then I'll say why that isn't satisfactory to me. So I feel like that there is this metacognitive belief aspect of flexibility that some people, either through prior experiences or just the way they're built, are more interested in exploring and playing in mathematics, and they're driven to think about creative solution methods and alternative solution methods. I think there's individual differences in that, and some people just have more of that than others. And that would suggest that they're going to bring that attitude, those beliefs, no matter what discipline of math they're studying, and it's very trait-like. So that would be an argument for trait. But where I'm challenged is I feel like the different subdomains of mathematics are all so different, and that I'm not sure it carries over. So like in the US, we often talk about the difference. In our curriculum, algebra and geometry are still taught separately in separate years in most schools, and students have very different experiences in those. Some people really like algebra and hate geometry, and vice versa. So I'm not convinced that if this trait component were true, it would apply to both of those, because they're so different. And I think we could come up with many other examples. Like proving is a very different kind of activity than modeling, I think. And do we have different beliefs about what that looks like and why that's important, and does it transfer across those? So that's my question about trait. On the state side, on the performance side, as you said, we've seen that most clearly, that teachers can influence students' flexibility by what they do in class, by the curriculum they use, by the messages they send about what they value. So it's malleable. It's very malleable. And so that would suggest to me that there's a strong state, a strong performance component to it. And that's the one that feels most under my control, I guess, what I can have the most influence on. So that's what we've put our money in, if you will. But I don't want to ignore the other bit as well that is harder to change, not impossible to change, but harder to change. And also this more trait aspect, the other piece that worries me is that students' beliefs about mathematics, we know they are strongly influenced by their teachers' beliefs about mathematics. And so if I wanted to change these deeply held underlying beliefs about mathematics and flexibility among students, then I have this very hard job to do the same thing with their teachers first, and help the teachers become different in the way that they think about flexibility. And in the US, that's especially hard. We have a lot of trouble with, especially primary school teachers' beliefs about mathematics.
Yes. Any other questions?
Just a little comment, because my research very focused, very recent 辨识 just in Confucius is 举一反三, just give 1, you have 10 to the 3. have some flexibility. When we're teaching the students, it's traditional tradition, a very old wisdom. We practice very widely in the classroom, but we seldom to realize it's an important part, important principle. Yeah. We apply very broadly, but we seldom editing. For the teacher education, I think is I supervise a thesis about the compare the expert teacher and the new teacher. There are differences, totally different, because the expertise is a good way, but bad teacher don't read. He make confused. He didn't understand the difference. Yeah, he always says it's wrong.
Yeah.
But I think it's a very important direction for us to reflect what we have done, how to prepare teacher better. Yeah, just a little comment.
Yeah. Well, I think. Go ahead.
The textbook comparison. For example, the American textbook only one way. Only one way is a station. The problem, station solution, just one way. In most textbook I read, yeah. But in Chinese, always there are two way, three way.
Yeah. So a couple of comments. So one is that in the past 20 years since we've been doing this work, I think there's been a lot of change to U.S. textbooks. So 20 years ago, I would agree with you that it was unusual for U.S. textbooks to show more than one way. Less so now. We find many more examples. And I think in the Chinese textbooks, it's been more consistent that you've shown multiple strategies than we have in the U.S. I think there's an important nuance to the ways in which multiple strategies are shown in textbooks that we've explored and written about, which is that I think when a textbook shows multiple strategies, there should be some point that it hopes to make by showing the multiple strategies. And the point I'm especially interested in is having students think about which strategy is better and why it's better, because that's to me about flexibility. There may be other points that are important, like a more conceptual point, or they maybe use different representations, so those are valuable. But I think this piece about which strategy is better and why, I feel like that's essential. And that's the piece that was most lacking in US text. So when you found multiple strategies shown in US text 20 years ago, it was infrequent, but when you saw it, it was sort of introduced without a seeming purpose. It was sort of like, oh, isn't this interesting? These students think about things differently. How interesting. And that's not bad, but that's not enough. Because I feel like that it should also reflect this disciplinary value of there being a difference in goodness, if you will, in elegance between these strategies. And it's not to say that we don't value the strategies that are less elegant. It's more that this idea of elegance is core to what mathematics is, and we want students to engage with it. So that's one kind of comment. The second is, I think one of the reasons, there's many, but one of the reasons that China is such an interesting context for me as a researcher is that this notion of variation theory, as you point out in your work and as you just said, is so deeply embedded culturally here. And it's something that all teachers understand to some extent, either because they were exposed to it in their teacher training, or perhaps more commonly because they were students here. They experienced it as a student. And so I think that's interesting for me to investigate, because I'm not sure from my very limited knowledge and my zero cultural knowledge of what goes on here, I'm not sure how specific and concrete that really is here. That I think teachers can all say a little bit about what that means, but if you say exactly what does that look like in your teaching, they would say, oh, I show students multiple strategies. And I say, well, exactly how do you pick those strategies, and what's the discussion you have about them? What does it really look like? And my starting hunch is that many teachers may not be able to answer that question. It's sort of just vague. And I'm not sure that that achieves the benefits that are desired within the variation theory idea. That's something that I want to learn more about, is to what extent does it really have very concrete implementation? And how do teachers learn about what that is? And are there differences? We have a similar phenomenon in the US, but it's not about variation theory. It's about what we would call constructivist teaching. So if you go into any classroom and you say, have you heard of constructivist teaching? All the teachers say, yeah, oh yes, definitely. And everyone has heard of it. And you say, where have you heard about it? And they say, oh, in my teacher education classes, and I experienced it when I was a child. And they would say, what exactly is that? What does that mean? And most teachers would say, they don't have a good answer to that. And so I feel like that's my starting hunch, that there may be a little of that going on here, but with variation theory. But that could be proven wrong.
Thank you very much. That's a very comprehensive coverage of flexibility research. I have a few questions or comments, but I will talk one first, then I wait for my colleagues or students here to be flexible to listen to questions. By seeing a very comprehensive coverage of flexibility research, because I think you mentioned pedagogical influence on teaching, on development of flexibility, or you also mentioned psychology or textbook research, especially shared, and also you mentioned culture and social influence. So probably you can organize a forum or conference just for flexibility research, or maybe a conference was the theme being flexibility. Anyway, this is I was inspired by your talk. So it's an area you try to establish, so related to different dimensions, areas. So maybe something, certainly we cannot organize because we don't have enough experts. If you want us to help, we can use logistics or planning. Anyway, I think it's a big area. Thank you for sharing your expertise and your knowledge of this. I also learned a lot. I'm particularly, impressed, or I agree with you, why study flexibility? Because if students became more flexible in solving problems, the task performance will be better. So you can say this to Chinese parents, because Chinese parents want to their kids to score high in Gaokao. But but I think flexibility is particularly helpful when students encounter difficulties in solving tasks. So sometimes students don't know how to switch. So sometimes the teacher will say, hey, you shouldn't be so, not so, I had a question, quotation mark, not be so stubborn, 固执 or 死脑子 in Chinese, right? That's Chinese culture. Somehow, 老师 they are good, they want to help. So you need to be 灵活, so 灵活性. So We have a lot of examples, but what I want to challenge you is sometimes there is only one unique solution. Different from Pythagoras or Pythagorean theorem, you have more than 400 ways to prove. But in my personal experience, I did have some mathematical research. I will not mention polynomial derivation, but I will mention this equality. Can you imagine? If A, B, C are all positive numbers, then A over B plus C plus B over A plus C over A plus B is larger than or equal to, do you know the answer? Do you know? Maybe I should use in Chinese to explain. 假如说 A、B、C 三个数都是正数 positive， 说 A 除以 B 加 C plus B 除以 A 加 C plus C 除以 A 加 B 是大于等于，你们知道什么吗？大于等于什么？大于等于3/2。大于等于3/2。我们 A equals B equals C equals yes equal 是说大于等于3/2。So over 3 over 2.
Right.
Yeah. Then it's very difficult to prove. I agree with you. Sometimes it's very elegant. So I published in 1993 in a Chinese math bulletin. So when I link what you talk to with concrete questions, I don't know if your flexibility theory can be applicable. You know, in the 一堂章是 proof of twin prime numbers. So narrow down. Now they say narrow down to 246 or 248. I don't remember exactly. So two prime numbers cannot be, the difference cannot be larger than, yeah. So I guess this is just one way. I don't know. So maybe the process is flexible if you encounter difficulty switch. But eventually there's only one way. So finally my question, sorry I took too long time. I have a lot of questions I will come to after.
Yeah.
Finally, I think I do agree with you. You have two main features for flexibility. One is multiple strategies. Students need to know multiple strategies. Multiple is more than one, so that's fine. But when you mention the other, you still need to know what's the most appropriate strategy. But I think this is dependent on a lot of factors. To you, maybe this is the most best strategy, but to Xing, maybe it's different. So it depends on personal knowledge, flexibility. So how would you?
Yeah, I agree. I think sometimes people ask that question as a way to argue against the importance of flexibility. They sort of question the existence of the appropriate idea at all. They say it's all relative. What you think is appropriate is different from what I think is appropriate. I don't disagree that it's nuanced, that we may differ, but for me that doesn't mean that it's not important, because I think that's true about mathematics as a discipline generally, that the point in arguing about which of two proofs is most elegant, for example, the point is that the two mathematicians may never agree about which of these two proofs is most elegant. They may go to their grave disagreeing about which of these two. But they can agree that both of these two are more elegant than these 10. So even though elegance is so difficult to define objectively, and even though they don't agree about the best strategy, they understand that there's aesthetics involved and they have some agreement about these are better than these. And so that's what I want for students. It's not that every problem has one best strategy and we have to agree on what that is, but I want students to see that optimization is an important feature of mathematical problem solving, and that by learning multiple methods, they can start to see which methods are most optimized and which methods are least optimized, And as a teacher, my obligation is not to accept any strategy they come up with, but to try to push them a little bit toward optimizing their solutions. So I think that's the bigger point. And the fact that in some of the problems I study, you can identify one best strategy that's better than one other strategy, that's just an artifact of the research method, that I have to simplify things in order to study them. But in the real world of doing mathematics, it's always going to be two subsets, like this subset of strategies is more elegant or better than this subset of strategies, and that mathematicians will all agree on that. And I think that's what we want students to start to see.
Do you have any questions? If you want to speak Chinese, I can go translate.
Hello, Professor John. I have a question. I started to wonder the relationship between among memorization and flexibility and creativity. So I want to ask a question. So during your study, is there any sign you can tell when students, when they do mathematics, they're using different strategy? It's come from memorization or come from creativity to build their flexibility ability. So I'm wondering if there any sign we can tell they're doing the math problem fluently, but whether they memorizing the answer, the strategy, or they just creativity, so they can become flexibility. So I think it's very important in education.
Yeah, thank you. That's a great question. So I do think we have ways to try to figure that out in our studies, although I'll make a little change. Instead of talking about memorization, which for me memorization is talking about a particular way that you get knowledge inside your head. And so in our studies, we're not so interested in whether they memorized or they got it in there some other way. We just want to know whether it's knowledge they have or whether they're generating it in a creative way as it's not knowledge they have, it's new things. Because I think that's at the core of your question, is whether we have a way to tell whether when we ask students to give us multiple ways, whether they're just telling us more strategies they know already, or whether they're inventing new strategies, all new. So the way that we do that experimentally is we try to ask students questions that exhaust their knowledge as best we can. So they will solve a problem, and then when we say, can you solve it another way? If they can give us another way, then that's knowledge. And then we might say, can you give us another way? And if they can do so quickly and easily, that's knowledge as well. It's only if they get to a point where they seem to be struggling and they can't come up with another way, then maybe we think what comes next is something they created or invented. So I think it's a little subtle because maybe students are doing that very quickly and it's hard to tell whether they're telling you what they know or whether they're inventing something. But that's what we've tried to do. Or we may ask them a multiple choice question that they have to answer, and we try to make the question to try to tell the difference. It's imperfect, but that's another way we try to do it as well. But this gives me a chance to talk about how I view the difference between creativity and flexibility, because that's also at the core of your question. So when I think of creativity, I think of generating novel strategies. But it's lacking this judgment that the discipline brings about which strategies are better. So let's imagine that I give students a problem to solve, and let's imagine that they produce a strategy that is about this long, sort of metaphorically. Think about it as this long. And then I give them another strategy that they produce one that's this long. So I could say they're creative because that one that's this long, I've never seen that before. Wow, that's interesting. That's unique. That's creative. But they're not being flexible because this strategy, in terms of my interest in optimization, is not good. This is better. And so creativity it's anything they produce. You can be creative. It doesn't have to be good. It just has to be novel. But flexibility is prioritizing whether they can produce strategies that disciplinarily we think are better and more appropriate. So I think that's the difference. And so I agree that when you get to higher math and really, really hard problems that no one has been able to solve, then that gets a little more tricky, because maybe that's where creativity is essential, because you do have to produce something that no one's ever seen before. But in school mathematics, I'm not sure creativity is as much of an emphasis for me, but flexibility is. But I know we could talk about this more.
Yeah, for the question, it's a great question. Yeah.
I think we have time for one last question. Or when do you take this chance?
Okay, so I really, because you see last one I didn't ask. Also for basically Professor Lee can answer. Professor Lee is the chair professor in science education.
Yeah.
So you see, I'm in mass education. So but I found that a lot of things we did in our study on mass education can be somehow applicable to science education, like a technology development, like a textbooks, or even measurement theory or whatever. But can you use your flexibility in science?
I actually have the same question.
Yeah.
So can you apply your theory to teaching science, teaching chemistry,
To all the subjects, yeah.
So
It's a very subjective reason.
yeah, so I think my answer right now is no. So I think that if we were talking about what psychologists call cognitive flexibility, then yes, that's a sort of general cognitive capacity.
Right.
It has to do with your ability to switch tasks, inhibit things, and that executive functioning. So that applies to everything. But I think flexibility for me is one of the answers to the question about why we teach mathematics in school. And I don't expect that the answer is going to be the same for why we teach science in school. So for example, some science educators might say we teach science in schools because it helps us understand the regularities and generalities about how our world works. They may say it helps us understand the scientific method and how we draw conclusions and make hypotheses from data. So there's great answers to this question that are very specific to science. And I think that there's other answers to this question about mathematics. I'm trying to answer those questions in mathematics because I think we are historically, traditionally, very bad at answering this question about mathematics. Science educators, I think, have great answers. But math educators, when students say, why do we need to learn math at school, then sometimes the best we can come up with is it's on the test. Or sometimes we say, oh, mathematics, it's very useful to your real life. But I disagree with that, actually. I don't think mathematics in general is useful. That much of what you learn in school, maybe someone somewhere is using it in some job, but that's not why we teach it. So we need other answers to why we learn mathematics. And part of this interest in elegance and flexibility is part of my answer to that question.
Can I make some comments real quick? Great question. I agree with what you said. I think in science, maybe in other subjects as well, flexibility may not be that important. But one common aspect across all the subjects, math, science, other subjects, is understanding, right? And flexibility seems to be manifestation of understanding. Understanding is common for all subjects, right? So in science, we look at student problem solving. We really look at how they understand. Right? So if we talk about understanding, and that is a common.
I don't disagree with that. I mean, I think I might wonder whether that moves us to a a level of generality that gets less useful. Because I think like my notion of flexibility, as you heard, is tightly linked to strategies. It's about how you solve problems and your knowledge of those strategies. And you could say, yes, well, I'm sort of interested in you understanding those strategies in a particular way. That's true. And that's the understanding connection. But I know that, like in mathematics, we think about this distinction that we often use. I talked about conceptual and procedural knowledge, but that's basically this distinction between principles and ideas and procedures and algorithms and strategies. And those are related to each other, but we think sort of in terms of the knowledge, in terms of the epistemology of mathematics, we think those are different things. And I feel like we have, in mathematics, we've spent a lot of time thinking about the principles and ideas side of things and how that's so important. And that's where understanding is used in mathematics education, about those principles and ideas. And my work is trying to focus our attention on the other part, on the procedures and the strategies, and saying those are important too, and how do we know those? And I think in science, if you have this content process distinction, which is the way it's talked about sometimes in science education, then I think in science, my sense is that you have a different set of priorities and historical debates about the relative importance of content and process. Even though we also have content and process, it's a different set of arguments. And so that's a way that I view those as different, that I am a process guy. Like I am pushing for how do we think about understanding a process. Whereas I'm not sure that's really what the push is in science education. But it's an interesting thing that I love talking about. Yeah.
It was deeper thinking, a lot of things behind.
Thank you very much.